Somewhere in the Milky Way there is a planet where it rains liquid iron. Not as a figure of speech, actual molten iron condensing into droplets and falling through a sky so hot it glows. And that planet is real. It has been measured. Its atmosphere has been studied. Scientists watch the data come in and realise that planetary weather could be far stranger than anyone had imagined. That is the kind of galaxy we live in. For most of human history we had no way of knowing this. We looked up at the night sky and saw stars, points of light scattered across darkness. Whether those stars had planets, whether those planets had atmospheres or storms or anything resembling weather at all, we simply couldn't tell. Then that began to change. New telescopes, better instruments, years of careful measurements, and slowly, one by one, distant worlds started to reveal themselves. What they revealed was not just variety, but strangeness. Planets with multiple suns, planets hotter than some stars, worlds with winds faster than sound, with glass rain, with skies we barely know how to describe. This is not a list of curiosities. It's an exploration of just how inventive the universe can be. We're going to take our time with this. Let's begin. Let's start with something that took astronomers a surprisingly long time to confirm, not because the evidence was difficult to find, but because the question itself felt almost too obvious to ask seriously. Do other stars have planets? It seems like a question with an obvious answer. Of course they do. Our Sun has 8 of them. Why would our Sun be special? Why would the laws of physics, which operate identically everywhere we've ever looked, produce planets here and nowhere else? It would be a staggering coincidence, and yet for most of the 20th century, actually proving that other stars had planets turned out to be remarkably difficult, not impossible, just difficult. Because planets do not shine. They do not broadcast their presence across light years of space. They are small, dark, and almost always completely overwhelmed by the brightness of whatever star they happen to orbit. The first confirmed detection of a planet outside our solar system did not come where most people might expect. It did not come from a bright sun-like star somewhere in a nearby constellation. It came from a pulsar, a neutron star, the collapsed rotating remnant of a star that had already exploded, sitting about 1,000 light-years away in the constellation Virgo. In 1992, astronomers Alexander Volshan and Dale Frail were studying this pulsar, catalogued as PSL 1257+12, when they noticed something unusual in its timing signals. Pulsars are extraordinarily precise in their rotation, some of the most accurate natural clocks in the known universe, but this one had a very slight wobble, a periodic variation in the arrival time of its pulses that could only be explained by the gravitational tug of orbiting companions. There were planets there, 2 of them, later found to be 3, circling a dead star in a system that should not, by any intuition, have been hospitable to planet formation at all. It was an unexpected beginning to the age of exoplanet discovery, and it set a tone that has persisted ever since. Whatever scientists expect the universe to do, the universe has other plans. The first planet found around a sun-like star came 3 years later, in 1995. Michel Mayor and Didier Queloz, working at the Observatoire de Haute-Provence in France, detected a planet orbiting the star 51 Pegasi, a star very similar to our own Sun, located about 50 light-years away in the constellation Pegasus. The planet they found was enormous, comparable in mass to Jupiter, and it was orbiting its star at a distance so close that its year, the time it took to complete a single orbit, lasted just over 4 Earth days. 4 days. This was not what the models predicted. According to everything astronomers understood about how planetary systems form, a gas giant of that size should not exist so close to its star. There was simply not enough material at that distance in a young solar system to build a planet that large. The prevailing theory held that gas giants had to form far out in the cold outer regions of a protoplanetary disk, where icy material could accumulate and where there was enough raw material to build something Jupiter-sized. And yet here was one, practically sitting on top of its star. What Mayer and Queloz had found was eventually called a hot Jupiter, and the discovery of 51 Pegasi b, as the planet came to be designated, did not just add a new world to the list, it forced a fundamental rethink of how planetary systems come to be. If gas giants could exist in tight orbits around their stars, then something had to move them there. Some mechanism, what scientists would later call planetary migration, had to be capable of taking a massive planet that formed far from its star and dragging it inward across billions of kilometres until it ended up where nobody expected it. The universe, in other words, was not following the script. Mayer and Queloz were eventually awarded the Nobel Prize in Physics for their discovery in 2019. By then, the world they had found was no longer remarkable for being the only one of its kind. It had become the prototype for an entire class of planets. A class that, as we will see, includes some of the strangest environments ever measured anywhere in the known universe. But to understand why some of these planets are so bizarre, it helps to first understand how we find them at all. Because the methods used to detect exoplanets are in themselves a quiet kind of miracle. The most productive method for finding exoplanets does not involve looking at the planets directly. It involves looking at their stars and watching for the subtle effect that a passing planet has on the light reaching us. When a planet orbits a star in an orientation that happens to take it across the face of that star from our perspective, what astronomers call a transit, it blocks a tiny fraction of the star's light. The dimming is usually less than 1%, sometimes far less than that. But with sensitive enough instruments and patient enough observation, it can be detected, and when it repeats, at regular intervals, it confirms the presence of an orbiting world. This method, the transit method, was the engine behind the Kepler Space Telescope, which launched in 2009 and spent nearly a decade staring at a single patch of sky containing roughly 150,000 stars. It was an act of extraordinary patience. Kepler did not move, it did not scan, it simply watched, and over the course of its mission, it detected thousands of candidate planets, most of which were later confirmed. The elegance of the transit method is matched by its limitation. It only works when a planetary orbit is aligned in just the right way, edge-on from our perspective. The vast majority of planetary systems are tilted at angles that make transits impossible to observe from Earth, which means that for every planet Kepler found, there were presumably many more in the same neighbourhood that it simply could not see. The confirmed count of over 5,500 exoplanets, which is where we stand at the time of writing, is almost certainly a dramatic undercount of the true population. There is another method worth understanding because it reveals things the transit method cannot. This is the radial velocity method, sometimes called Doppler spectroscopy. When a planet orbits a star, it does not simply circle a stationary object. Both the planet and the star orbit their shared centre of mass, which means the star itself moves in a tiny but measurable way. As the star moves toward us, the light it emits is compressed, blue shifted. As it moves away, the light is stretched, red shifted. By measuring these tiny shifts in a star's spectrum, astronomers can infer the presence of a planet they cannot see, and even get a rough estimate of that planet's mass. This is the method Mayer and Queloz used to find 51 Pegasi b, and it remains one of the most powerful tools available, particularly for detecting massive planets close to their stars, because those planets exert the strongest gravitational influence. Between these two methods and a handful of others, gravitational microlensing, direct imaging, astrometry, we have built a picture of the exoplanet population that would have been unimaginable a generation ago. And the picture that has emerged is one of extraordinary variety. Some of that variety falls within the range of what we expected. Rocky planets with solid surfaces, gas giants with thick atmospheres, worlds at just the right distance from their stars to potentially harbour liquid water. These exist, and in large numbers. But they're not what this story is about. This story is about the outliers, the planets that made astronomers stop mid-sentence and reconsider their assumptions, the worlds at the edges of what physics seems to permit, and occasionally beyond them. Let us begin with the ones that are perhaps hardest to picture, the worlds defined by heat. WASP 76 sits about 640 light-years away from us, in the direction of the constellation Pisces. It is a gas giant, roughly comparable to Jupiter in size, though somewhat larger. It orbits its star at a distance of about 4 million kilometres, a small fraction of the distance between Mercury and our Sun. A year on WASP 76b lasts about 43 Earth hours. At that distance, the planet is subjected to radiation levels that dwarf anything in our solar system. The day side, the hemisphere that permanently faces the star, because WASP 76b is tidally locked in the same way our moon is locked to Earth, reaches temperatures of around 2,400 degrees Celsius, hot enough to vaporize iron, hot enough to break apart the molecular bonds in most compounds we know of, reducing complex chemistry to a relatively simple mixture of atoms and ions. But the night side is cooler. Not cold, still around 1,400 degrees, but significantly cooler than the day side. And that temperature difference drives winds. Enormous, fast winds that circulate from the day side to the night side, carrying material from one hemisphere to the other. Here is where things become interesting. On the scorching day side, iron in the atmosphere exists as a vapour. Iron atoms floating freely in the superheated gas. Those atoms are swept by the high-altitude winds toward the cooler night side, and when they cross the terminator, the boundary between the day and night hemispheres, the temperature drops enough that iron can condense, not as a solid, but as droplets, a liquid. The result, according to observations made with the European Southern Observatory's Very Large Telescope and published in 2020, is that the evening terminator of WASP 76b experiences precipitation of liquid iron rain, falling from clouds made of condensed metal vapour, coming down through an atmosphere still far hotter than the interior of a furnace. The researchers detected this using a technique that measures the Doppler shift of iron absorption lines in the planet's atmosphere as it transits its star. On the day side, the iron signal was blue shifted, indicating the gas was moving toward the observers, toward us, as the winds pushed it from the day side into the terminator. On the night side, the iron signal weakened considerably, suggesting that the iron had condensed and rained out before making it all the way around. It is one of the most striking single observations in the history of exoplanet science, not just because of what it tells us about WASP 76b specifically, but because of what it tells us about the range of atmospheric processes that are possible under conditions unlike anything in our own solar system. WASP 76b is not alone in this category. WASP 121b, another hot Jupiter, about 850 light-years away in Puppis, has been found to have an atmosphere containing water vapour, as well as signatures of other heavy metals. Its dayside temperature exceeds 2,500 degrees Celsius, and the temperature difference between its two hemispheres appears to drive a jet stream that carries material rapidly around the planet. Observations with the Hubble Space Telescope have detected what appears to be a stratosphere on WASP 121b, a layer of the atmosphere where temperature increases with altitude rather than decreasing, likely caused by the absorption of intense stellar radiation by certain atmospheric compounds. Then there is HD 209458b, sometimes called Osiris, a planet that has been studied for so long and in such detail that it has become a kind of benchmark for the entire field. Osiris is a hot Jupiter orbiting a star about 159 light-years away, and it was the first exoplanet to be confirmed through the transit method back in 1999. Detailed observations have revealed that its atmosphere is being stripped away by the intense radiation from its star. The outer layers are being hydrodynamically evaporated, blown off into space in a comet-like trail. The planet is losing mass, slowly, by stellar standards but measurably. Whether it will survive long enough to become a Chthonian planet, a bare, rocky core stripped of all its gas, or whether it will eventually fall into its star is still an open question. Hot Jupiters collectively represent one of the great puzzles of modern planetary science. They appear to be relatively rare, occurring around perhaps 1% of Sun-like stars, but their formation and evolution has forced repeated revisions to planetary formation theory. The current understanding holds that they formed far from their stars, in the cold outer reaches of their young solar systems, and then migrated inward through interaction with the protoplanetary disk or with other planets. But the details of how this migration works, how fast it happens, and what determines whether a planet stops its inward journey or continues all the way into its star are still being worked out. And in the process of working it out, scientists have found that hot Jupiters are just the beginning of what heat can do to a world. One of the more subtle patterns to emerge from the exoplanet census is something called the hot Neptune desert. It refers to a statistical gap in the population of known exoplanets. There are very few Neptune-sized planets orbiting extremely close to their stars. The gap is not absolute. A handful of examples exist, but it is noticeable enough to suggest that something systematic is happening. The leading explanation is photoevaporation. Planets in tight orbits around their stars are bombarded with radiation. If a planet is massive enough, like a hot Jupiter, its gravity is strong enough to retain its atmosphere even in the face of this radiation. But Neptune-sized planets sit in an awkward middle ground. They are not massive enough to hold on completely, and the radiation is intense enough to strip their atmospheres away over millions or billions of years. The end result would be a smaller, denser planet, a super-Earth, perhaps, with little or no gas envelope remaining. This is sometimes called the photoevaporation valley or the radius gap. There is a range of planetary radii, roughly between 1.5 and 2 times Earth's radius, where few planets are found, presumably because planets of that size tend to either retain their atmospheres and remain larger, or lose them entirely and shrink down. The gap is a kind of absence that tells a story about atmospheric loss. But there are exceptions. Planets in the hot Neptune desert that somehow survived. One of the most striking is LTT 9779b, a planet about 260 light-years away that sits firmly in the middle of where the desert is supposed to be. It is Neptune-sized, orbiting at a distance that gives it a year of about 19 Earth hours, and its dayside temperature has been measured at around 2000 degrees Celsius, hot enough to be comparable to some low-mass stars. What has puzzled researchers about LTT 9779b is not just that it exists in the desert, but what its atmosphere appears to be made of. Observations from the Cheops and Spitzer space telescopes revealed that the planet has an extraordinarily high albedo. It reflects a large fraction of the starlight that hits it. On the day side, this reflection appears to come from clouds made of silicate and metal compounds. The same kind of extreme chemistry found in hot Jupiters, but in a smaller planet that, by rights, should have been stripped bare long ago. Why it survived is still unclear. One hypothesis is that the planet formed in an unusual environment, perhaps inheriting an exceptionally heavy, metal-rich atmosphere from its parent disk that proved more resistant to evaporation than typical compositions. Another is that the reflective cloud layer itself plays a role in its survival, bouncing enough radiation back into space to reduce the rate of atmospheric stripping. LTT 9779b is an outlier in the best possible way, a world that exists precisely where it should not, doing precisely what it should not be able to do, and in doing so, asking questions that existing models cannot yet fully answer. Not all extreme exoplanets are defined by their proximity to a star or their atmospheric conditions. Some are extreme in their fundamental composition, in the very materials they are made of. In our solar system, the rocky planets, Mercury, Venus, Earth, and Mars, share broadly similar compositions: silicate rock, iron cores, oxygen-bearing minerals. The ratios vary, but the basic palette is the same. That palette reflects the composition of the Sun, which itself reflects the composition of the interstellar cloud from which our solar system formed. Different stars have different compositions, and different compositions in the planetary disk that forms around a star can produce dramatically different kinds of worlds. Consider a star with a higher ratio of carbon to oxygen than our Sun. In such a system, the chemistry of the protoplanetary disk changes significantly. Instead of silicate minerals, the dominant building blocks of Earth and its neighbours, you get carbide minerals, silicon carbide, graphite, and under high enough pressure, deep in the interior of a large enough planet, you might get something else entirely. You might get diamond. 55 Cancri is a super-Earth, a planet significantly larger and more massive than Earth but still in the rocky category, orbiting a binary star system about 41 light-years away in the constellation Cancer. It was one of the first super-Earths to be studied in detail, and early analysis of the system's composition suggested that the planet could be composed largely of carbon. If that were true, and it is worth noting that subsequent research has introduced some uncertainty here, then beneath the surface of 55 Cancri E, under pressures generated by its own mass, carbon could be compressed into crystalline form, diamond in quantities that would dwarf anything in the Earth's crust by a factor beyond meaningful comparison. The planet is not habitable in any conventional sense. It orbits its star at a distance of only about 2.5 million kilometres, giving it a year of roughly 18 Earth hours, and its surface temperature has been estimated at somewhere around 2000 degrees Celsius. Any diamond that exists there is far beyond reach, buried beneath layers of rock and compressed carbon in a planetary interior that no instrument we have could probe directly. But the concept matters for what it implies about diversity. If the chemistry of a planet's host star can produce a world whose interior is fundamentally different from anything in our solar system, carbon instead of silicate, diamond instead of iron ore, then the range of what a rocky planet can actually be is far wider than Earth's neighbourhood suggests. More recent work on 55 Cancri E has complicated the picture somewhat. Spectroscopic observations from the James Webb Space Telescope, which launched in December 2021 and has been transforming exoplanet science ever since, have suggested that the planet may have a volatile atmosphere, something not expected for a world so close to its star and so hot. The atmospheric signature detected is complex, and the composition is still being debated. What this demonstrates more than anything is that individual planets are more complicated than simple categories suggest. 55 Cancri E continues to be one of the most intensively studied exoplanets precisely because it keeps offering data that does not fit neatly into existing frameworks. The idea of planetary diversity, that worlds can be built from fundamentally different raw materials than anything in our own solar system, is one of the recurring themes of modern exoplanet science, and it reaches perhaps its most dramatic expression not in the chemistry of individual worlds, but in the environments around which they form. Most people who grew up watching science fiction have seen a scene in which a character stands on the surface of a distant world and watches two suns set simultaneously below the horizon. It is one of the iconic images of the genre. For most of the history of astronomy, it was assumed to be just that, an image, a piece of visual poetry, a shorthand for alienness. Then, in 2011, the Kepler Space Telescope confirmed that it was real. Kepler 16b was the first exoplanet confirmed to orbit not one star, but two, a binary star system, two stars locked in a mutual gravitational dance, with a planet circling around the outside of them both. From the surface of Kepler 16b, if you could stand there, you would watch two stars move across the sky, sometimes close together, sometimes more separated, but both undeniably present, casting overlapping shadows, creating days with two different twilights, and nights that varied in darkness depending on where in the sky those two suns happened to be. The discovery was significant not just romantically but scientifically. For a long time, it was genuinely unclear whether stable planetary orbits were possible in binary star systems. The gravitational situation is complicated. Two stars in orbit around each other create a constantly shifting gravitational landscape. A planet circling one star tightly, what astronomers call an S-type or a circumstellar orbit, might survive if it stays close enough to its own star that the other star's influence remains weak. A planet circling both stars together, a P-type or circumbinary orbit, might survive if it stays far enough out that the central binary appears as a single combined gravitational source. But planets in between, in the region where the two gravitational fields compete most directly, those would likely be ejected, scattered out of the system entirely or hurled into one of the stars. Kepler 16b is in a circumbinary orbit, circling both stars together, well outside the instability zone. It is roughly the size of Saturn, and it orbits at a distance similar to Venus's distance from the Sun, though its year is somewhat longer because the combined mass of its two stars is less than our Sun's mass. The system it lives in has a certain elegance to it. The two stars orbit each other every 41 days, and the planet's orbit is tilted at just the right angle to produce transits across both stars, which is what allowed Kepler to detect it. Since Kepler 16b, a growing number of circumbinary planets have been confirmed. Kepler 34b, Kepler 35b, Kepler 47, a system remarkable for containing multiple planets in a circumbinary configuration, and others. The population is still small compared to planets around single stars, in part because the detection methods are more complicated, but the existence of these worlds has established that planetary formation is robust enough to succeed even in environments that seem, at first glance, hostile to it. The dynamics of life on a circumbinary planet would be unlike anything familiar from Earth. The day-night cycle would be irregular in complex ways, because the amount of light you receive depends not just on where your planet is in its orbit, but on where each of the two stars is relative to you at any given moment. Seasons, if they existed, would be driven not just by orbital tilt, but by the changing configuration of two heat sources. The sky, at times, would show two distinct solar disks. At other times, they might overlap, creating a brief period of double brightness before separating again. Eclipse events would happen frequently. When one star passes in front of the other, the light drops suddenly and temporarily. When your planet's orbit takes it between the two stars, it shadows one from the other. The celestial mechanics would produce a sky that was, by Earth standards, in constant interesting motion. Binary stars, it turns out, are only the beginning of the multi-star story. A significant fraction of stellar systems contain not two stars, but 3, 4, 5, or more. The organisational principle that keeps these systems stable over long timescales is hierarchy, a nested structure in which close pairs orbit each other quickly, while those pairs orbit more distant companions more slowly, and the whole system maintains a delicate but durable equilibrium. In a triple star system, for example, you typically find two stars in a close binary configuration, with a third star orbiting the pair at a much greater distance. From the perspective of the third star, the close binary looks, in terms of gravity, something like a single object. The three-body problem, the notoriously complicated mathematics of three mutually gravitating objects, is somewhat tamed by this hierarchy. It does not go away, but the system remains predictable over astronomical timescales. Four-star systems take the hierarchy a step further. You might have two binary pairs, each orbiting the other, or a triple system with a fourth star circling the whole ensemble. Real examples of this kind of structure have been found. and the complexity of the stellar environments in which planets might form and might survive grows with each additional star. So where might a planet sit in a 5, 6 or 7 star system? The answer depends entirely on the hierarchy. A planet in a tight orbit around one of the innermost stars in such a system might have only one sun in its sky in any meaningful sense. With the other stars so distant they appear merely as bright stars rather than solar disks. A planet in a wide outer orbit around the entire system would see all its constituent stars, though they might be small and dim. This is where it becomes possible to imagine with genuine scientific grounding the scenario of a planet with 7 suns. The hierarchical structure of a 7-star system creates multiple niches where planets could potentially survive. A planet in the outermost stable orbit around the entire system would, in principle, see all 7 stars, though they would be separated into their respective subpairs, appearing as clusters of light rather than individual disks. The total illumination might still be modest compared to a single nearby star. No confirmed planet with 7 stellar companions has yet been found, but the stellar multiplicity observed throughout the galaxy makes such a system a reasonable possibility, and the confirmed existence of planets in increasingly complex multi-star environments has shifted the question from "is this possible?" to "how do we find one?" It is worth sitting with that shift for a moment. Not long ago, a planet with even 2 suns seemed like pure fiction. The mathematical objections were real. The detection methods did not yet exist, and so the question was largely left to imagination. Then the instruments improved and the question became observational. And it turned out that nature had been building these worlds all along, without waiting for us to think them possible. That pattern, the universe being ahead of our predictions, repeats itself throughout the history of exoplanet discovery. It will repeat itself several more times before this story is over. There is a category of planetary object that challenges the very definition of what a planet is, not by virtue of its composition or its orbit, but by the absence of something we tend to consider fundamental. A rogue planet has no star. It drifts through interstellar space, unattached to any stellar system, moving on a trajectory set long ago by whatever gravitational encounter sent it wandering. It receives no meaningful light, no warmth, no radiation from a nearby source. If it has a surface, that surface is perpetually dark and cold, at least in any conventional sense. The existence of rogue planets was theoretically predicted well before any were confirmed. The same simulations that describe planetary migration, the process by which planets move inward or outward within a stellar system, also suggested that not all migrations would end neatly. Some planets, the model showed, would be scattered out of their original systems entirely. Gravitational interactions with larger planets, particularly during the chaotic early period of a planetary system's formation, could send smaller planets on trajectories that took them past the edge of their star's influence and out into the open void. How common this process is, how many rogue planets exist for every star in the galaxy, has been a subject of considerable debate. Some estimates, based on gravitational microlensing surveys, have suggested that rogue planets may be extremely numerous. A 2011 study using data from a gravitational microlensing survey called MEOA suggested that there might be nearly 2 Jupiter-mass rogue planets for every star in the Milky Way. More recent work has revised those estimates in various directions, but the broad consensus is that rogue planets are not rare. The galaxy may contain more of them than it contains stars. The challenge of detecting them is obvious. Without a star to illuminate them or to be perturbed by them, rogue planets are essentially invisible to most detection methods. Gravitational microlensing, the brief brightening of a background star when a massive object passes in front of it and focuses its light, is the primary tool available, and it requires careful, sustained monitoring of millions of stars simultaneously. Some potential rogue planets have been confirmed, or at least strongly suspected. OGLE 2 016BLG1928 is one of the smallest candidates detected through microlensing, with a mass estimated at less than 1 Earth mass. Potentially a roughly Earth-sized object drifting free in the galaxy. Others are much larger, in the sub-brown dwarf range. The question of what a rogue planet is actually like is fascinating precisely because it is so hard to answer. For a rocky rogue planet, the scenario is clear enough. An airless or near-airless body at temperatures near absolute zero, with no energy source to speak of, drifting in permanent darkness. But for a larger rogue planet, one with a massive gaseous envelope, or one with a significant internal heat source from residual formation energy or radioactive decay, the situation might be more nuanced. Some researchers have speculated that a sufficiently large rogue planet could maintain a form of subsurface warmth long enough, over billions of years, for interesting chemistry to occur. If such a planet retained enough hydrogen in its atmosphere to create a greenhouse effect, even a modest internal heat source might keep temperatures at the boundary between the atmosphere and the solid surface above the freezing point of water for extended periods. This is speculative, and the probability seems low. But the mere fact that it is not physically impossible is striking. The possibility that life might exist on a planet with no star at all, sustained entirely by internal heat and an insulating atmosphere, is one of the more quietly unsettling implications of rogue planet science. For now, rogue planets remain at the frontier of detectability. The Roman Space Telescope, NASA's upcoming Wide-Field Infrared Survey Telescope, is expected to detect hundreds or possibly thousands of rogue planet candidates through microlensing, which will dramatically improve our understanding of their population, their masses, and their frequency. The picture that will emerge from that survey is one of the things the field looks forward to most. One of the more humbling aspects of the exoplanet census is the discovery that the most common type of planet in the galaxy does not exist in our solar system. Super-Earths, planets larger than Earth but smaller than Neptune, with radii typically between 1 and 4 times Earth's radius, are abundant. They appear around stars of all types. They come in a dizzying variety of orbital configurations. They are the most frequently detected category of exoplanet in the Kepler data, and there is no compelling reason to think they are less common in the galaxy as a whole. Our solar system has nothing in this range. Earth, the largest rocky planet, has a radius of 1. Neptune, the smallest ice giant, has a radius of nearly 4. The gap between them, the space where super-Earths and mini-Neptunes sit, is simply empty in our neighbourhood. This might reflect something special about how our solar system formed, or it might be an accident of sampling in a galaxy full of variety. Either way, it means that our intuitions about planets, built entirely from what we see in our own neighbourhood, are systematically missing the most common type. Super-Earths come in 2 distinct flavours that are sometimes difficult to distinguish from the outside. Those with a significant gaseous envelope, mini-Neptunes, can look observationally similar to those without one. The distinction between a dense, rocky super-Earth and a smaller gassier mini-Neptune is not always visible in the basic measurements of size and mass. Atmospheric characterization, measuring the composition and depth of a planet's atmosphere, is needed to tell them apart, and that requires detailed follow-up with instruments like the James Webb Space Telescope. Among the super-Earths that have been studied in enough detail to say something definitive, the range of environments is striking. TOI 700d, discovered by NASA's TESS mission in 2020, is a rocky super-Earth about 100 light-years away that orbits within the habitable zone of its star, the range of distances at which liquid water could potentially exist on the surface. It has attracted attention as one of the more realistic candidates for further study, with the caveat that its star is a red dwarf and comes with the associated complications of stellar flares and potential atmospheric stripping. K218b, some 124 light-years away in Leo, is another frequently discussed super-Earth, though its classification has been revised repeatedly as new data arrived. It sits in the habitable zone of its red dwarf star and observations with the Hubble Space Telescope detected water vapour in its atmosphere, the first detection of water in a super-Earth atmosphere in the habitable zone. Subsequent observations with the James Webb Space Telescope detected carbon dioxide and methane, and tentatively identified a molecule called dimethyl sulfide, a compound that, on Earth, is produced almost exclusively by biological activity. The researchers who reported this result in 2023 were careful to note that it was a tentative detection and that non-biological sources could not yet be ruled out. But the finding generated considerable discussion, and K218b has become one of the most watched targets in the field. What makes K218b particularly interesting is its likely interior structure. At its size and mass, it may be what some researchers call a Hycean world, a planet with a thick hydrogen-rich atmosphere overlying a global ocean of liquid water. The concept of a Hycean world was proposed relatively recently, and it represents a category of potentially habitable environments that had not previously been considered in detail. If planets like this are common, and initial estimates suggest they might be, then the range of environments where life could potentially emerge is considerably wider than most earlier models assumed. Consider what happens to a planetary system when its star dies. For a star like the Sun, the end comes in stages. After several billion more years of fusing hydrogen in its core, the Sun will exhaust its central fuel supply and expand dramatically into a red giant. During this expansion, the inner planets will be engulfed. Mercury and Venus will almost certainly be consumed. Earth may survive, though it will be scorched beyond recognition. The outer planets will remain, their orbits altered by the sudden change in the Sun's mass as it sheds its outer layers. Eventually the red giant phase ends. The Sun's outer layers drift away into space as a planetary nebula, a glowing shell of expelled gas, illuminated briefly by the hot core left behind. That core is a white dwarf, a compact, dense remnant about the size of Earth, but with a significant fraction of the Sun's original mass, now slowly cooling over billions of years. This is the fate of the vast majority of stars in the galaxy. All stars below a certain mass threshold will end as white dwarfs. And for a long time, it was assumed that whatever planetary systems existed around those stars would be largely disrupted or destroyed in the process. The story turned out to be more complicated. White dwarfs have been found with atmospheres polluted by heavy elements, silicon, iron, calcium, that should not be there if the white dwarf was simply radiating energy from a pure hydrogen or helium envelope. The most natural explanation for this pollution is accretion. Rocky material, asteroids, comet fragments, possibly disrupted planets, is falling onto the white dwarf's surface and being absorbed into its atmosphere. The spectral fingerprint of this infalling material has been measured in many white dwarfs, and it provides a direct way to sample the composition of the rocky bodies in those systems. But more directly relevant to planetary science is the confirmation that some white dwarfs host surviving planets. The most striking example to date is WD-1856+534b, a gas giant planet about 7 times the mass of Jupiter, orbiting a white dwarf about 80 light-years away. It was discovered through the transit method. The planet passes in front of the white dwarf, causing a detectable dimming, and its orbit is extraordinarily close to its host star, with a period of just over 34 hours. The fascinating question is how it got there. The planet's orbit is far inside the region that would have been engulfed by the expanding red giant phase of the white dwarf's progenitor star. Something moved it inward after the star died, or it was in a very different configuration during the giant phase and was brought close later by gravitational perturbations. The exact mechanism is not yet known, and the planet's survival is a potential model for how planetary systems persist and change through the death of their stars is one of the more profound open questions in current planetary science. There's also growing evidence that planets can form around white dwarfs, or at least that debris disks. the raw material from which planets are built, can persist around them. A handful of white dwarfs have been found with infrared excess emission, indicating warm dust in tight orbits, consistent with a debris disk from disrupted bodies. Whether that material could organise itself into new planetary structures over time is speculative, but not impossible. And then there are the pulsar planets. Back to where we started this story. PSR 1257+12, the pulsar discovered in 1992, has 3 confirmed planets orbiting it, with orbital periods ranging from 25 to 98 days. Pulsars are neutron stars, the collapsed cores of massive stars that ended their lives in supernova explosions, and the environment around them is ferociously hostile in ways that go beyond anything we have discussed so far. The neutron star spins rapidly, and in doing so emits intense beams of radiation that sweep across anything nearby with every rotation. How the planets around PSR 1257+12 came to exist is still debated. One hypothesis is that they formed from the disk of material left over by the supernova explosion that created the neutron star. Another is that they were once planets around a companion star that was consumed, and that they have orbited the pulsar since then through complex gravitational history. Either way, these planets, if indeed they are planets and not something else, experience an environment entirely unlike anything in our solar system, bathed in pulsar radiation in a system that began in catastrophe. They persist nonetheless. They orbit on in the ruins of what was once a star. Saturn's rings are one of the most iconic sights in the solar system. When you see them for the first time, really see them, through a telescope, as actual rings, and not just a textbook picture. There is something that happens in the mind that is hard to describe. They are vast. They extend tens of thousands of kilometers from the planet's surface, yet they are paper thin by cosmic standards, in places just tens of meters thick. They are made of ice and rock ranging in size from grains of dust to boulders, all orbiting together in an extraordinary flat disk. And then you hear about J1407b. J1407b is an object. Its classification is still somewhat uncertain. It may be a giant planet or it may be a small brown dwarf, orbiting a young sun-like star designated J1407, located about 430 light-years away in the constellation Centaurus. What makes J1407b remarkable is not the object itself, but what surrounds it. The ring system of J1407b, inferred from observations made in 2012 and subsequently analysed in detail, is approximately 200 times larger than Saturn's rings. Not 200 times wider in proportion, 200 times larger in absolute scale. Where Saturn's rings extend to about 140,000 kilometres from the planet's centre, J1407b's ring system appears to extend to tens of millions of kilometres. It contains dozens of distinct ring bands, some of which show clear gaps that may have been cleared by moonlets orbiting within the ring structure. A direct echo of the same process that creates the gaps in Saturn's rings, but at a scale that is almost difficult to comprehend. If J1407b's ring system were placed around Saturn, the rings would be clearly visible to the naked eye from Earth, appearing as a disk in the sky that spanned many times the apparent diameter of the full moon. They would cast a ring shadow over a portion of the sky that would change with the seasons. They would be a visible feature of the night sky. The rings appear to be in a relatively early stage of evolution. The mass estimated to be within the ring system is consistent with what you might expect if moons were in the process of forming. Rings have accreted over time into increasingly organised structures, and a young massive ring system around a giant planet might represent the early phase of a process that eventually produces a family of natural satellites, much as Jupiter's large moons are thought to have formed from a disk of material that once surrounded the young giant planet. If this interpretation is correct, and there is still considerable uncertainty, then what J1407b's rings represent is not just a strange world, but a process. A giant planet in the act of building its moons, playing out on a scale that our own solar system's history was too fast or too slow for us to observe directly. Other candidates for large ring systems have been identified, though the evidence is less compelling. The transiting behaviour of some stars has shown complex dimming patterns consistent with extended ring structures around orbiting objects. The difficulty is that the same patterns can sometimes be explained by other things: dust clouds, debris, stellar variability, and confirming a ring system as definitively as J1407b requires both a well-characterised transit event and enough additional observations to rule out alternatives. Saturn's rings are thought to be geologically young, probably no more than a few 100 million years old, perhaps much younger, which raises the question of where they came from. The leading hypothesis involves the tidal disruption of a moon that strayed too close to Saturn, or a collision between moons. This suggests that rings are not permanent features of giant planets, but dynamic, transient structures on cosmological timescales. If that is true of our solar system, then J1407b's massive rings may be a temporary spectacle as well. Grand and spectacular now, but slowly evolving, the material gradually coalescing into moons or drifting away, the universe offering a brief window onto a process that most planetary systems go through, in a form we cannot observe from our current vantage point in time. There is a quality of light that Earth's surface sees only at certain specific moments, just after sunrise or just before sunset, when the sun is close to the horizon and light arrives at a shallow angle, filtering through a longer path of atmosphere and spreading a kind of amber glow across the landscape. Photographers call it the golden hour. It lasts at most 30 or 40 minutes before the sun rises too high or sets completely. For some planets, that is all there ever is. Tidally locked planets, worlds that orbit their star so closely that the same hemisphere always faces the star as the moon always faces the same side toward Earth, have a permanent day side and a permanent night side. In between, there is a narrow band where the star always hangs near the horizon, a ring of perpetual twilight circling the planet like a belt. For planets in the habitable zone of small cool stars, red dwarfs, tidal locking is extremely common. Red dwarfs, sometimes called M-dwarfs, are the most numerous type of star in the galaxy, making up roughly 3/4 of all stellar objects. They are long-lived, burning their hydrogen fuel at a slow and steady pace for tens or even hundreds of billions of years, and their habitable zones, the range of orbital distances where liquid water might persist, are close in because the stars are faint. Planets in those habitable zones are so close to their stars that tidal locking is almost inevitable. This creates a particular kind of world. The day side receives constant, unrelenting illumination. The night side sits in permanent darkness. The temperature difference between the two hemispheres drives atmospheric circulation, strong winds flowing from the hot day side to the cold night side, redistributing heat and potentially preventing the night side from freezing completely. Whether those winds are enough to prevent the night side from becoming a cold trap, a region where atmospheric gases freeze out, gradually reducing the planet's total atmosphere, is one of the key questions in red dwarf habitability research. Climate models suggest that for some atmospheric compositions, the circulation can sustain a relatively stable climate across much of the planet's surface, with the most extreme conditions confined to the substellar point, the patch of surface directly beneath the star, where the sun hangs permanently overhead, and the anti-stellar point on the opposite side in permanent darkness. Temperatures between those extremes in the Terminator band might be surprisingly moderate. Proxima Centauri b, the closest known exoplanet to Earth at just over 4 light-years away, orbits in the habitable zone of Proxima Centauri, the nearest star to our Sun. It is likely tidally locked. It is also subject to regular intense flare activity from its host star, which complicates the habitability picture considerably. Whether it has retained an atmosphere capable of sustaining moderate surface conditions in the face of those flares is unknown. Direct detection of its atmosphere, if it has one, awaits instruments beyond what is currently available. TRAPPIST-1 is a red dwarf star about 40 light-years away that has become perhaps the most discussed stellar system for habitability beyond our own. It contains 7 known planets, all of them rocky, with 3 sitting within or near the habitable zone. The innermost planets are almost certainly tidally locked. The system has been observed in extraordinary detail. The James Webb Space Telescope has been used to search for atmospheric signatures on several of the TRAPPIST-1 planets, and while definitive atmospheric detections have not yet been announced, the system remains a primary target for the next generation of atmospheric characterization work. The TRAPPIST-1 system is remarkable not just for the number of habitable zone planets it contains, but for what it implies about planet formation around small stars. 3 potentially habitable worlds in a single system is a statistic that demands attention. It suggests that such worlds are not anomalies but common outcomes, that red dwarfs, which are by far the most abundant stars in the galaxy, are surrounded by rocky planets in abundance, and that the habitable zones of those stars are populated. The question of what it would actually be like to stand on one of those worlds, in the Terminator band, watching a small dim red sun balance permanently on the horizon, casting long shadows across a landscape whose sky is always in the same deep amber glow, is one that researchers have begun to model with increasing sophistication. The answers suggest a world of quiet stability in the visual sense, always the same angle of light, always the same position of the star, but with weather driven by the temperature gradient between day and night, creating complex patterns. A sky that is, in some ways, more dynamic than Earth's, even as the star itself never moves. For every planet that is too dense for comfort, there exists a counterpart that is almost too light to believe. Superpuff planets, a term that began informally in the astronomical literature and has since become standard, are worlds whose density is so low that it challenges current models of planetary structure to explain them. The canonical example is Kepler-51b, a planet discovered in the Kepler data and subsequently confirmed and characterized in detail. It is slightly larger than Jupiter, but has roughly 100 times less mass. Its density has been measured at about 0.1 grams per cubic centimetre. This is about 1/10 the density of water. It is, in the most literal physical sense, a planet that would float in a large enough bathtub. The density of a planet reflects the balance between its gaseous envelope, which is extended and light, and its rocky core. Earth, which has no significant gaseous component to speak of on the scale of planetary density, is about 5.5 grams per cubic centimetre. Saturn, which is mostly gas, has a density of about 0.7 grams per cubic centimetre, famously low enough that it would float in water too, at least theoretically. But Kepler-51b is at a factor of 7 below Saturn. How does this happen? The most widely accepted explanation involves the interplay of the planet's equilibrium temperature and the behaviour of its gaseous envelope. Kepler-51b orbits relatively close to its star, and the stellar radiation heats its outer atmosphere, causing it to puff up significantly beyond the equilibrium radius that simple models predict. The result is an enormous, distended, gossamer-thin atmosphere extending thousands of kilometres above whatever denser core sits at the planet's centre. Additional superpuff planets have been found in subsequent surveys, and each new characterization adds to the puzzle. Kepler-18d, Kepler-79d, and a few others all have densities that require explanation. The challenge is not just that they are light, it is that their extended atmospheres make them harder to study. The thickness and diffuse nature of the envelope means that observations of atmospheric absorption features are spread over a larger area, diluting the signal. Atmospheric characterization of superpuff planets requires combining multiple techniques and accumulating observations over longer periods. Some researchers have proposed that superpuffs are undergoing significant atmospheric escape. that they are actively losing their outer layers through photoevaporation and represent a transitional phase between large, puffy planets and smaller, denser remnants. Under this interpretation, what we're observing is not a stable long-term configuration, but a snapshot of ongoing atmospheric loss, which would explain both the current extended state and why these planets appear to exist primarily in tight orbits, where stellar radiation is most intense. Others have suggested that the answer lies in the presence of high-altitude aerosol or dust layers, a kind of permanent atmospheric haze that gives the planet a larger apparent radius without adding significant mass. This would affect our radius measurements without altering the mass, producing an artificially low density estimate for what is actually a more normal planet. Both explanations may be partially correct. Superpuffs may represent a category of planet that can arise from different pathways, but that all share the common feature of possessing extended low-density gaseous envelopes in a state of active evolution. The precise mechanisms are still being worked out, and the arrival of better atmospheric data from James Webb has been helping to distinguish between competing models. There is a category of astronomical object that sits awkwardly between planet and star, defined less by its internal physics than by how it formed and where it sits in a hierarchy. This is the brown dwarf, an object more massive than even the largest gas giants, but not massive enough to sustain the hydrogen fusion that makes a true star. Brown dwarfs glow with residual heat from their formation, gradually cooling over billions of years, and they occupy a kind of twilight zone between planetary and stellar physics. The boundary between giant planets and brown dwarfs is not sharp. It is usually placed around 13 Jupiter masses, the minimum mass needed to briefly fuse deuterium, a heavy form of hydrogen. But this threshold is physically somewhat arbitrary, and large giant planets and small brown dwarfs can be difficult to distinguish observationally. What this means practically is that some of the objects detected in tight orbits around stars and designated as planets are objects whose surface temperatures rival or exceed those of low-mass stars. Kelt 9b, arguably the most extreme confirmed hot Jupiter known, orbits a star about 650 light-years away with a period of just under 36 hours. Its dayside temperature has been measured at approximately 4,050 degrees Celsius, hotter than many stars, including all red dwarfs and many orange dwarfs. The stellar radiation breaks apart molecular hydrogen in its atmosphere into individual atoms, and some of the heavy elements detected in its spectrum, iron, titanium, barium, exist as ions rather than neutral atoms, a condition that in most contexts we associate with stellar atmospheres rather than planetary ones. Kelt 9b is categorised as a planet because it formed in a disk around a star, not through the direct gravitational collapse that forms true stars and brown dwarfs, but its atmospheric physics have more in common with a stellar atmosphere than with anything in our solar system. It is, in some sense, a planet masquerading as a small star, or a small star in a planet situation. The study of ultra-hot Jupiters like Kelt 9b has opened up a branch of planetary science that borrows heavily from stellar physics. Techniques developed to understand stellar spectra have been applied to planetary atmospheres that are chemically and thermally more similar to stars than to conventional planets. The crossover has been intellectually productive, with each field offering tools and insights to the other. It also raises, in a philosophical if not strictly scientific sense, the question of what a planet actually is. The International Astronomical Union's official definition, adopted in 2006 and most famous for reclassifying Pluto, applies only to our solar system. For exoplanets, the definitions are less precise. In practice, objects below about 13 Jupiter masses that form in a disk are called planets. Objects that form through direct gravitational collapse are called brown dwarfs or stars, depending on their mass. But nature does not always respect the cleanliness of our categories, and the boundary between these regimes is a subject of ongoing discussion. What Kelt 9b and its ultra-hot siblings make clear is that planet is not a single thing. It is a category that encompasses an enormous range of objects, from cold, rocky bodies like Mars to scorching gas giants with stellar temperature atmospheres and everything in between. The range is wide enough that the label sometimes obscures more than it reveals. At the cooler end of the planetary temperature spectrum, still far outside anything we would call habitable, but not in the realm of molten metal, lies a set of worlds whose atmospheric chemistry carries particular interest. The detection of specific molecules in an exoplanet's atmosphere is one of the primary goals of the current generation of space telescopes. Not just because knowing what an atmosphere is made of tells us about the planet's formation and evolution, but because certain molecules, particularly certain combinations of molecules, are associated with biological activity in ways that are difficult to explain through purely chemical processes. Methane and oxygen coexisting in an atmosphere, for example, represent what chemists call a disequilibrium chemistry. Methane reacts with oxygen. In the presence of both compounds and ultraviolet radiation, the methane should be destroyed over relatively short timescales. Finding both together in an atmosphere therefore implies an ongoing source of methane production, something that is continually replenishing it, faster than the chemical reactions remove it. On Earth, the ongoing source of atmospheric methane is almost entirely biological. Methane is produced by microbial life in enormous quantities, particularly in anaerobic environments. This does not mean that wherever we find methane in an exoplanet atmosphere, we have found life. Non-biological methane sources exist, volcanic outgassing being the most obvious. And in a planet with no oxygen to react with, methane can persist indefinitely from purely geological sources. The biosignature case is most compelling when methane and oxygen are found together, because that combination is harder to explain without biology. Carbon dioxide, methane and water have all been detected in exoplanet atmospheres, with varying degrees of confidence. The James Webb Space Telescope has raised the quality of atmospheric characterization dramatically. Its infrared sensitivity allows it to probe molecular signatures that previous instruments could not resolve, and in the few years since its launch, it has delivered atmospheric detections of unprecedented clarity. The detection of carbon dioxide in the atmosphere of WASP 39b, a hot Saturn-type planet about 700 light-years away, was announced in 2022 and represented the first clear infrared detection of carbon dioxide in an exoplanet atmosphere. It was a technical milestone more than a scientific surprise. Carbon dioxide was expected to be present. But the precision of the detection demonstrated what Webb is capable of, and set the stage for the more scientifically consequential measurements to come. The TRAPPIST-1 planets, as mentioned, remain primary targets for atmospheric characterization with Webb. Early results have been mixed in terms of providing clear atmospheric detections, but the observations are ongoing. The challenge is that the stars in question are active. They flare, and those flares can mimic atmospheric signals. And the atmospheric signatures are at the limit of what even Webb can resolve. The scientific community's expectation is that definitive results, one way or another, will emerge within the next several years of observing time. What the search for atmospheric chemistry and habitable zone planets ultimately represents is the convergence of two questions that have occupied human curiosity since we first looked at the night sky. Are we alone? And if not, where? The tools to begin providing observational answers to those questions now exist. They are being used, and the answers, when they come, will reshape the discussion in ways that are genuinely difficult to predict. At the upper extreme of planetary size, there is a world called HATP 32b. It orbits a star about 950 light-years away, and has a radius about twice that of Jupiter, roughly 20 times Earth's radius. It is one of the largest exoplanets confirmed by direct transit measurement. Its density is remarkably low, as one might expect for an inflated hot Jupiter, and its atmospheric temperature is high enough that the models that predict how gas giant radii scale with temperature and mass are pushed to their limits. There is also ROX 42b discovered through direct imaging, one of a small number of planets found not by their effect on their host star, but by actually detecting their emitted infrared light. It orbits at a very large distance from its host star, putting it in a realm where the distinction between giant planet and brown dwarf becomes particularly murky. Its formation history is poorly constrained. The record for confirmed exoplanet size tends to change with new detections, and the upper limit is physically set by the point at which an object becomes massive enough to fuse deuterium, the boundary of the brown dwarf regime. But within the confirmed planet population, the largest worlds occupy a striking parameter space. They are often less massive than they appear, because inflation has stretched their radii far beyond what their mass alone would predict. The physics of inflated hot Jupiters has been a subject of extended theoretical debate. The basic question is why some planets are larger than models predict, given their known mass and irradiation. The answer is not fully settled, but leading candidates include the deposition of stellar energy deep into the planet's atmosphere through processes like ohmic heating, the dissipation of electrical currents induced by the planet's magnetic field moving through the ionized gas, and the suppression of convective cooling by the intense irradiation from above. What this means, practically, is that the size of a giant planet is not a simple function of how much material is in it. The environment it lives in, particularly how close it is to its star, changes its physical properties profoundly. The same amount of material placed at different orbital distances produces measurably different planets. This context dependence of planetary properties is one of the most important lessons exoplanet science has delivered. There is no such thing as a planet in isolation, divorced from its stellar environment. We have spoken of planets whose years last hours, but the other end of the timescale is equally interesting. The distance at which planets can orbit while remaining gravitationally bound to their stars is in principle very large. A planet in an extremely wide orbit, thousands of astronomical units from its host star, would take millions of years to complete a single circuit. It would spend the vast majority of its orbit in the cold outer reaches of the stellar system, rarely approaching the star closely enough to be detectably affected by its warmth. The direct imaging method has revealed a number of planets at very large orbital separations, tens or hundreds of astronomical units from their host stars. These are among the most difficult to form, according to conventional disk accretion models, because the density of material at those distances should be too low to build a planet within the lifetime of the disk. Alternative formation mechanisms, direct gravitational collapse, or capture from a passing stellar system, have been proposed, and the precise formation pathways for wide-orbit giant planets remain an active area of research. There is also a category of object whose year is defined not by its orbit around a star, but by its orbit around the galaxy. The Milky Way takes about 225 to 250 million years to complete one rotation, as measured by the position of our solar system. This is sometimes called a cosmic year, or a galactic year. In this timescale, the Earth is roughly 18 galactic years old, a teenager by that measure, even after 4.5 billion Earth years. A planet in the very outer reaches of a wide stellar orbit might have a year that approaches the galactic year in length, though no confirmed example of this extreme exists. What these timescales reveal is the sheer range of rhythms the universe operates on, from hot Jupiters, with years shorter than a single Earth day, to hypothetical wide-orbit giants whose years stretch across epochs of geological time. The concept of a year, which feels so natural and fixed in our experience, is entirely arbitrary in the larger context of planetary physics. As detection methods improve, the boundary of what counts as found keeps extending outward. Gravitational micro-lensing events have detected exoplanets thousands of light-years away, far beyond the reach of the transit or radial velocity methods, which require either specific geometrical alignments or relatively nearby stars whose spectra can be measured in enough detail to detect tiny Doppler shifts. The Kepler and TIRS missions have surveyed primarily the local stellar neighbourhood, within a few thousand light years in the case of Kepler, somewhat more varied in the case of TESS, which surveys the entire sky but focuses on the nearest bright stars. The Roman Space Telescope, targeting the galactic bulge for its microlensing survey, will probe a fundamentally different population, stars in the densely packed central regions of the Milky Way at distances of tens of thousands of light years. What might be found there, whether the planet populations in the galactic bulge differ from those in the disk, whether the dense stellar environment of the centre affects planet formation differently, is genuinely unknown. The survey will produce thousands of new candidates across a range of distances and stellar types that have never been systematically probed before. It represents the next major expansion of the exoplanet census. And beyond our galaxy, the first candidate exoplanets in other galaxies, tentatively detected through microlensing signals and observations of distant gravitational lensing events, suggest that planetary systems are not unique to the Milky Way. The evidence is indirect and the detections are not individually confirmed in the way that nearby exoplanets are. But the statistical implication is clear. Wherever there are stars, there appear to be planets. The closest spiral galaxy to our own, Andromeda, sits about 2.5 million light-years away. The notion of exoplanets in other galaxies is, for now, on the edge of what is measurable and what is merely inferable. But the inference is reasonable. The physics of planet formation does not depend on which galaxy you are in. The further we travel from the questions that can be given clear answers, the more the story becomes one of possibility rather than conclusion. From here, the ideas unfold more slowly. We have been moving quickly through a world of specifics, measured temperatures and confirmed densities, and named telescopes and dated discoveries. That specificity has been the point. The strangeness of these worlds is most vivid when it is grounded in actual observation, in data that someone actually collected with an actual instrument aimed at an actual star. But there is another dimension to the exoplanet story that does not yield to measurement quite so readily. It has to do with context, with what all of this data means when you take a step back and look at it together, with what the galaxy, viewed whole, appears to be. What the last 30 years of exoplanet science have quietly revealed is not just a population of strange worlds. They have revealed that the universe is engaged in something like an endless experiment in planetary formation, running variations on the same basic process under an enormous range of conditions, producing an enormous range of outcomes, and preserving those outcomes for billions of years in orbital configurations that are, in many cases, stable enough to last until the stars themselves run out of fuel. The variety is not random noise, it has structure. There are patterns in which types of planets form, around which types of stars. There are trends in how planet size relates to orbital period, how atmospheric composition relates to stellar chemistry, how system architecture relates to formation environment. The patterns are not perfectly understood. Each new mission produces results that both confirm parts of the picture and complicate others. But they are real, and they point toward a universe that is, in some deep sense, organised. An atmosphere is, among other things, a record. Not a complete record. Atmospheres change, gain molecules and lose them, are bombarded by radiation and replenished by volcanism and altered by whatever chemistry exists at the surface or within the body below. But at any given moment, the composition of a planet's atmosphere reflects the history of everything that has happened to it. What material it formed from, how close it has been to its star, what geological processes have been active, and potentially what biology has been producing for whatever time life has existed. The idea of reading a planet's atmosphere from light years away is remarkable when you stop to think about it. The light from a planet star passes through the thin strip of atmosphere visible at the planet's limb during a transit. Some wavelengths are absorbed by specific molecules in that atmosphere. By comparing the stellar spectrum during transit with the stellar spectrum outside of transit and measuring the difference, you can infer what molecules are present. The technique is called transmission spectroscopy, and it is one of the primary tools of atmospheric characterization. The atmospheres of hot Jupiters are the easiest to characterize. They are extended, high temperature, and in tight orbits that produce frequent transits, giving observers many opportunities to accumulate signal. Water, carbon dioxide, methane, sodium, potassium, titanium oxide, iron vapor all have been detected in various hot Jupiter atmospheres using this method. The diversity of compositions, even within the category of hot Jupiters, is striking. The same formation process, under slightly different initial conditions, produces atmospheres that are chemically quite different from one another. For smaller, cooler planets, the ones more likely to be habitable, the atmospheric signal is weaker and harder to extract. The planet's atmosphere is thinner and less extended. The transits are shorter. The signal to noise is lower. This is the challenge that Webb is working to overcome, with its larger mirror and its infrared sensitivity. The results will come slowly, but they will come. What strikes researchers about this work is the strange intimacy of it. You are, in effect, tasting the air of another world. The information is encoded in light that has travelled for dozens or hundreds of light years to reach your telescope. And in that light is the spectral fingerprint of molecules in an atmosphere you will never physically sample, on a world you will never visit, orbiting a star you cannot see without a telescope. And yet the chemistry is real, and the measurement is real, and what you learn from it is as concrete as anything in a laboratory. It is a form of knowing the universe that has no real precedent in human history, not just observing distant objects but characterizing them, learning what they are made of, how they move, how they evolved, what they might contain. The exoplanet era has made the universe not just larger in our awareness but richer in texture, more populated, more knowable. Of all the molecules that appear in atmospheric spectra, water draws the most sustained attention. This is partly scientific. Water is a tracer of planet formation history, as it freezes out at specific temperatures, and its distribution in a planetary system reflects where and how cold that system was during formation. And it is partly the other thing, the one that everyone in the field is aware of even when the discussion stays carefully technical. Water is associated, on the only inhabited world we know of, with life. The detection of water vapour in a habitable zone planet's atmosphere would not confirm the presence of life. It would not even suggest it very strongly, because water can be produced by purely geological processes and can persist in an atmosphere under a wide range of conditions. But it would confirm that liquid water could exist on the surface, under the right pressure and temperature conditions, which is a prerequisite that significantly narrows the field. The search for water in habitable zone atmospheres is among the highest priorities in the current exoplanet program. The James Webb Space Telescope has the sensitivity to detect water vapour in the atmospheres of the TRAPPIST-1 planets, provided those planets have atmospheres substantial enough to produce a detectable signal. Early observations of some TRAPPIST-1 planets have placed limits on atmospheric thickness, but have not yet produced definitive detections or non-detections. The observations are continuing. K218b, mentioned earlier, had water vapour detected in its atmosphere by the Hubble Space Telescope in 2019, the first confirmed detection of water in a habitable zone planet's atmosphere. The planet is too large to be rocky in the traditional sense. It is more likely a sub-Neptune with a thick hydrogen envelope overlying a potential ocean, but the detection was significant both technically and conceptually. It demonstrated that the atmospheres of habitable zone exoplanets were measurable, that water was detectable in them, and that the project of atmospheric characterization for potentially habitable worlds was not just theoretical but practically achievable. Webb's subsequent observations of K218b, published in 2023, went further. Carbon dioxide and methane were detected, and the tentative signal of dimethyl sulfide, biological molecule, appeared. The paper's authors were careful to note the tentativeness of the dimethyl sulfide detection, and the scientific community has been appropriately cautious about drawing strong conclusions. But the observation has not gone away. Follow-up observations are planned, and the result will either strengthen or weaken the case. What the K218b story illustrates is the way in which the search for life in the universe is slowly shifting from the theoretical to the empirical. Not quickly, not definitively, but genuinely, concretely, observation by observation. Each measurement narrows the uncertainty a little. Each new telescope generation opens possibilities that the previous one could not access. The pace of progress is slow enough to be frustrating if you're impatient, but fast enough viewed from the appropriate distance to be extraordinary. 30 years ago, we did not know of a single planet beyond our solar system. Today we know of thousands, have characterized the atmospheres of dozens, and have found at least one that shows a tentative biosignature molecule. The trajectory of this enterprise is clear, even if the destination is not yet in sight. A planet's character is not determined by the planet alone. The star it orbits shapes everything about it: the energy it receives, the radiation environment it lives in, the composition of the disk from which it formed. Different kinds of stars make different kinds of planets, and understanding the range of stellar types helps illuminate why the exoplanet zoo is so varied. Red dwarfs, as discussed, are the most numerous. Their long lifetimes and close habitable zones create a particular set of conditions for their planetary systems. Because they are faint, planets must orbit close to stay warm, which leads to tidal locking, flare exposure, and complex atmospheric dynamics. But the sheer number of red dwarfs in the galaxy means that the absolute number of habitable zone planets around them vastly exceeds the number around Sun-like stars, even if the individual conditions are challenging. Sun-like stars, G-type in the stellar classification system, produce environments most similar to our own. They are not the most common, but they are numerous and relatively well studied. Their habitable zones are at moderate distances, tidal locking is not generally an issue for planets there, and their activity levels are typically manageable. Our solar system, shaped by one of these stars, is the benchmark against which everything else tends to be measured. Larger, hotter, and more massive than the Sun, the A-type and F-type stars have shorter lifetimes and more intense radiation environments. They can still host planets, and confirmed exoplanets around these stars exist, but the intense ultraviolet output shortens the window during which surface life could develop, assuming it requires long timescales analogous to Earth's. Kelt 9b, the planet hotter than many stars, orbits an A-type star. Beyond those there are the giants, the hot blue and white stars that burn fast and die young in supernova explosions. Their planetary systems, if they manage to form, exist for only millions of years before the stars that define them end catastrophically. Yet even these environments may produce planets, and some of the white dwarfs left behind by their predecessors have been found with the signatures of planetary material still present. Each stellar type creates a different planetary context, and the exoplanet census, viewed through this lens, becomes a map of all the different ways a star can shape the worlds around it. The map is incomplete. Large regions are undersampled, and the biases of our detection methods have preferentially revealed some kinds of worlds over others. But the outline is increasingly clear, and it shows a galaxy where the production of planetary systems is not an exception to stellar physics, but a natural, almost inevitable accompaniment to it. Stars make planets, not always, not in predictable configurations, not with predictable results, but routinely, across the full range of stellar masses and ages and compositions. The universe is full of worlds. The strangeness of many of those worlds is a consequence of the conditions under which they formed, and those conditions vary as widely as the stars themselves. There is a particular kind of intellectual humility that good science cultivates, and it is this: the awareness that the absence of evidence is not evidence of absence, and that the maps we've drawn of the universe are necessarily incomplete, shaped as much by the limits of our instruments as by the true distribution of what is out there. We have found many extraordinary things in the last 3 decades of exoplanet science. Iron rain, and diamond interiors, and ring systems the size of solar systems, and planets circling dead stars, and gas giants heated at temperatures that challenge the meaning of the word planet. We have found evidence, tentative but real, of chemistry in distant atmospheres that bears noting even in the absence of certainty. And we have not found everything. The portion of the galaxy that our current surveys can access in meaningful detail is a small fraction of the total. The stellar systems that have been characterized in depth, whose planetary populations are known, whose atmospheric properties have been measured, number in the hundreds or at most the low thousands. The Milky Way contains somewhere between 100 billion and 400 billion stars. The gap between what we know and what exists is staggering. In that gap, by simple statistical extrapolation, there are trillions of planets, most of them ordinary, some of them extraordinary in ways we have already imagined and catalogued, and some, certainly some, extraordinary in ways we have not imagined, because we have not yet seen anything like them, and our imagination has not been prompted. The history of discovery is full of categories that did not exist before someone found the first example. Hot Jupiters did not exist as a concept until 1995. Superpuff planets were not a recognised class until Kepler revealed them. Rogue planets were theoretical until microlensing surveys began turning them up. Each new instrument, each new technique, each new survey has produced not just more examples of known categories, but entirely new categories, new kinds of strange. This will continue. The Roman Space Telescope, ESA's Plato mission, the extremely large telescope being built in Chile, the concept missions being designed now for launch in the 2030s and 2040s, each of these will see parts of the universe that no human instrument has seen before, at resolutions and sensitivities that will make things visible that are currently below the threshold of detection. What those instruments will find is unknown. That is not a rhetorical flourish, it is a genuine statement about the state of knowledge. The next decade of exoplanet science will produce results that cannot be predicted in detail, because they depend on what the universe has placed in corners we have not yet looked carefully into. That is one of the things that makes this era of astronomy what it is. The questions are not just large, they are genuinely open. Light from the Sun takes about 8 minutes to reach Earth. Light from the nearest star, Proxima Centauri, takes 4 years. Light from the TRAPPIST-1 system takes 40 years. Light from Kelt 9, the star that hosts the planet hotter than most stars, takes about 650 years. When we look at Kelt 9 with a telescope, we are seeing light that left that star in the 14th century, by Earth's reckoning. The planet Kelt 9b, in whatever state it is in now, is 650 years further into its story than what we can observe. Its iron-ionized atmosphere has continued in its tidal heat for all those years while we were building cathedrals and crossing oceans and doing all the other things that humans have been doing. There is something calming in that perspective if you let it settle. The universe is not waiting for us to observe it. The billions of worlds in the galaxy are living out their orbital lives at their own pace, in their own times, whether anyone is watching or not. The strange and beautiful physics that produces iron rain and diamond cores and tidally locked twilight belts is not a performance staged for our benefit. It is simply what happens when matter organises itself according to the laws that govern it, over timescales longer than any human concept of time can really hold. Our observations are brief glimpses. We open the aperture of a telescope, collect a few hours of photons, and from those photons we reconstruct a story. The temperature, the composition, the orbital history, the fate of a world. The reconstruction is astonishing in its precision given how indirect the evidence is, but it is always incomplete, always an approximation, always a story told from fragments. And yet the fragments add up. The picture, imperfect as it is, keeps getting richer. Each additional observation fills in a part of the image that was previously uncertain. Each new telescope opens a part of the spectrum that was previously invisible. The process is slow and patient and cumulative, and it has been going on long enough now to have produced a picture that would have been unrecognisable to the astronomers who first began thinking seriously about other worlds. When the number of known exoplanets crossed the 5,000 mark, an announcement made in March 2022, it prompted a kind of reflective pause in the scientific community. 5,000 worlds, each one a real place, somewhere out in the galaxy, with its own physical properties and its own orbital history, and its own relationship with the star that warms it or scorches it, or barely illuminates it at all. The number is simultaneously large and small. Large compared to what anyone imagined knowing when the century began, small compared to the estimated billions of planets in the Milky Way alone. Large as a collection of characterized, confirmed real objects, small as a sampling fraction. What the number communicates, more than any specific fact about any specific planet, is that planetary systems are not exceptional. They are the ordinary accompaniment to stars. The galaxy is a world-making machine that has been running for billions of years, producing planets around stars of every kind, at every distance, in every imaginable configuration. Some of those planets will be rocky and cold, drifting far from their suns in the silence of deep space. Some will be torched by radiation, their atmospheres blasted away or puffed to enormous extent by the star they orbit. Some will be sitting in the quiet middle distances where chemistry can proceed and complexity can accumulate. All of them are real. All of them are, in some sense, out there right now, orbiting their stars at whatever pace their orbital mechanics dictate, indifferent to whether we know about them. There is a peacefulness in that thought, if you approach it in the right way. Not the peacefulness of answers, but the peacefulness of a picture so large that your particular concerns find a natural sense of proportion within it. 5,000 confirmed worlds, and trillions more unobserved, each one following its orbital path with the precision of a clock, season after season, of its own peculiar calendar for billions of years. The history of how we came to know about these worlds is itself a kind of quiet epic. It begins not with a telescope, but with a question. What are stars? For most of human history, no one knew. They were lights in the sky, associated with seasons and navigation and mythology, but their nature was opaque. It was not until the 19th century that the tools of spectroscopy began to reveal that stars were made of the same elements found on Earth, that the same physics operated everywhere. That revelation, the unity of the cosmos, is one of the most profound in the history of science, and everything that followed, including exoplanet science, rests on it. Once it was established that stars were distant suns, the question of whether they had planets became natural. But it took a century more to develop the instruments sensitive enough to detect them. Planetary science, like most sciences, advances not in heroic leaps, but in long preparations followed by brief moments of sudden clarity. Years of building better spectrographs, designing better photometers, refining the analysis techniques for dealing with stellar noise, before suddenly the data quality crosses a threshold and confirmation becomes possible. The 1992 detection of pulsar planets and the 1995 detection of 51 Pegasi b were those threshold moments. They arrived not because someone had a brilliant new idea, but because the technology had finally caught up with a question that had been asked for decades. And once the first few were found, the accumulation accelerated. Better instruments found more planets. More planets revealed patterns. Patterns motivated new instruments and new missions. Each piece of the picture demanded the next piece. that accumulation is still ongoing. The James Webb Space Telescope, operating now in its cold halo orbit 1.5 million kilometers from Earth, represents the current leading edge of what is measurable. Its mirror, 6.5 meters across and made of 18 hexagonal gold-coated beryllium segments, collects infrared light from sources that no instrument before it could see in comparable detail. It has already delivered atmospheric detections and compositional measurements that were, a decade ago, considered aspirational targets, things that might eventually be achievable, given enough years and enough technical development. What it has not yet done is the thing many people in the field are quietly waiting for: a clear, confirmed, unambiguous detection of a biosignature in the atmosphere of a habitable zone planet. Whether that will happen in Webb's operational lifetime, expected to extend for at least 10 years, possibly longer, is unknown. Whether the TRAPPIST-1 planets have substantial enough atmospheres to produce detectable biosignatures is unknown. Whether biology, wherever it might exist in the galaxy, produces molecules in its atmosphere in the concentrations that Webb can detect at these distances is unknown. The uncertainty is real, but so is the capability. And the combination of real capability with genuine uncertainty is the most interesting scientific condition there is. Among astronomers who study habitability and biosignatures, there is a specific kind of target that exists not yet in the confirmed exoplanet catalogue, but in the planning documents for future missions. It is called informally an Earth twin, a rocky planet, roughly Earth-sized, orbiting a sun-like star at approximately the right distance for liquid water, with an atmospheric composition that includes oxygen, water vapour, and perhaps a trace of methane. No such planet has been confirmed. A handful of candidates exist, planets that satisfy one or two of the criteria, but the combination of sun-like star, Earth-sized planet, habitable zone orbit, and measurable atmosphere is beyond the capability of current instruments to confirm definitively. The rocky planets in the habitable zones of red dwarfs are the closest we can get at present, and they come with complications: flare exposure, tidal locking, atmospheric stripping, that make the question of habitability uncertain. The mission designed to find Earth twins around sun-like stars is not yet built. Concepts exist. The Habitable Worlds Observatory, proposed as the next-generation flagship mission after Webb, but they are in the early design phase, with a launch expected sometime in the late 2030s or early 2040s. The mission would be specifically designed to directly image Earth-sized planets in the habitable zones of nearby sun-like stars and to take their spectra, to read the chemistry of their atmospheres directly, not through transmission spectroscopy during transits, but through direct light from the planet itself. If such a mission succeeds, if it detects an Earth-sized planet around a nearby sun-like star and measures oxygen and water in its atmosphere, the implications are difficult to fully imagine. Not because we would immediately know whether life exists there, but because the question would no longer be theoretical, it would be empirical. We would be looking at a world that satisfied the known prerequisites for life as we understand it, and we would be asking of it the same kind of questions we ask of any world. What is it made of? What does its history look like? And what might be happening on its surface? The answer to the deepest version of that question, whether life of any kind exists anywhere besides Earth, is still unknown. It may not be answered in this generation or the next. The galaxy is large, and the detections are hard, and biology, even if it is common, may not always produce atmospheres with the specific signatures that our instruments can detect. But the direction of travel is clear. We are moving steadily and incrementally toward the capacity to address that question, observationally rather than theoretically. And the worlds we have found along the way, the iron rain planets and the diamond worlds and the giants orbiting dead stars and the soft twilight worlds at the edge of the habitable zone, are not just curiosities. They are context. They tell us the range of what is possible, and in doing so they help us understand where in that range the conditions for life might fall. There is an image that comes to mind when thinking about all of this. Not a photograph, but an impression. It is a clear night, far from city lights, and the band of the Milky Way is visible overhead, faint and dense, the accumulated glow of hundreds of billions of stars too close together to resolve individually. Every point of light in that band, every individual star you can see, and the countless ones you cannot, is a sun. Many of them have planets. Many of those planets are strange in ways we have catalogued here. And many more are strange in ways we have not yet imagined. We look at that sky and we know now, in a way that no generation before ours could have known with the same degree of empirical confidence, that it is full of worlds, that the universe did not build suns only to leave them alone, suspended in space like bare bulbs in an empty room, but surrounded them with the complex, varied, endlessly surprising products of orbital mechanics and chemistry and time. The strangeness of those worlds is not a sign that the universe is alien or hostile or beyond understanding. It is a sign that physics is rich, and that given enough variation in initial conditions, the same fundamental laws produce an extraordinary range of outcomes. Iron rain follows naturally from the temperature difference between a tidally locked planet's two hemispheres, given the right atmospheric composition. Diamond interiors follow from the right carbon-to-oxygen ratio in the original disk. Pulsar planets follow from the mechanics of supernova remnants and their associated material. Everything is explicable in principle. The strangeness is not the strangeness of the incomprehensible, but of the unfamiliar, of possibilities that our local experience had not prepared us for, but that turn out, on examination, to arise from the same physics we know. That is perhaps the most hopeful thing the exoplanet era has produced. Not any individual discovery, however spectacular, but a deepened confidence that the universe is, at its foundations, knowable. That patient observation and careful analysis and the gradual accumulation of data will, over time, bring even the most distant and alien-seeming worlds into a framework of understanding. That the strangeness, as it is examined, resolves not into chaos but into order, a wider, richer, more surprising order than we initially expected, but order nonetheless. And with that thought resting gently in the background, the thought of a galaxy full of worlds, each one following the same physics in its own particular way, each one accumulating its own long history in the dark between the stars, it becomes possible to let the story settle into itself. Consider for a moment what it actually took to get here. The people who built the spectrographs and the photometers, who stayed up through cold observatory nights, accumulating hours of signal from stars so faint they barely registered. The engineers who designed the thermal shielding for the James Webb Space Telescope, knowing that a single leak in the system, a single point of thermal contamination, would render the entire instrument blind. The scientists who spent years writing the proposals that justified the missions, who had to argue with numbers and simulations and projections that the universe would, in fact, contain something worth finding once the instruments were pointed in the right direction. They did not know for certain. They had good reasons to think so, but certainty was not available to them. They proceeded anyway, on the strength of evidence and intuition, and the accumulated tradition of a science that has been rewarding patience for 4 centuries. Galileo turned a small refracting telescope toward Jupiter in 1610 and saw 4 points of light that moved. He tracked them night after night and concluded they were moons, bodies orbiting Jupiter the way the moon orbits Earth, the way the planets orbit the sun. It was one of the observations that helped shift the intellectual weight of centuries toward a sun-centered cosmos. But Galileo had no way of knowing, looking at those 4 moving points, that the question of moons would eventually extend to every planet in the solar system and then beyond. That centuries later, we would not only be counting the moons of other planets, but cataloguing the planets of other stars and measuring the chemistry of their atmospheres, and debating whether a molecule detected in the spectrum of a world 100 light-years away might be the product of living things. The chain from Galileo's moving points to JWST's atmospheric detections is long, and it passes through hundreds of individual acts of curiosity and patience and technical ingenuity. Each link in that chain was, at the time it was forged, the frontier. Each astronomer who pushed the instruments a little further asked a question that had not been asked before, built a method that had not existed, was doing what scientists have always done, extending the reach of the knowable by one careful step. We are in one of those steps right now. The current moment in exoplanet science is not the beginning, and it is not the end. It is somewhere in the long middle of a project whose full scope we cannot yet see. And that middle is a remarkable place to be, past the stage of merely proving that other worlds exist, not yet at the stage of being able to say with confidence what they harbour. In the space between those two milestones, there is an enormous amount of interesting, careful, open-ended science to do. There is also something worth naming about the experience of knowing this, of being a person alive at a moment when the question of other worlds has shifted from the philosophical to the observational. It changes something about the texture of looking up at the sky at night. When you see the constellation Aquarius rising in the east, somewhere in that direction, at a distance of about 39 light-years, is the TRAPPIST-1 system. 7 rocky planets orbiting a dim red star that your naked eye cannot even resolve as a point of light. 3 of those planets are in or near the habitable zone. We know their sizes, we know their masses, we know roughly how much radiation they receive. We are actively trying to determine whether they have atmospheres. That knowledge is not visible to the naked eye. The star is too faint, the planets invisible, the 39 light-years an untraversable distance given any technology we currently possess or can presently imagine possessing. But the knowledge is real, and it sits in your mind as you look at that part of the sky, and it changes what the darkness means. The darkness is not empty. It is full of specifics. It contains things we have named and measured and argued about in scientific papers. The universe you're looking at when you look up has more texture and more detail in it than any previous generation of humans could have known. That is a gift, and it is worth recognizing it as such. The expansion of the knowable is not inevitable. It is the product of choices. To fund telescopes, to train scientists, to maintain the institutional structures that allow long-term projects to proceed across decades, to preserve the tradition of basic research that produces no immediate practical benefit, but that, over time, produces the most profound shifts in how we understand where we are and what we are part of. We are part of a galaxy that has been making planets for nearly as long as it has existed. The first stars formed within a few 100 million years of the Big Bang, roughly 13.6 billion years ago, and while those early stars were very different from the Sun, made almost entirely of hydrogen and helium with virtually no heavier elements. Later generations of stars were enriched by the material those early stars expelled when they died. Each generation of stars left behind more complex elements, carbon, oxygen, silicon, iron, that became the building blocks for the generation after them, and for the planets that formed around that next generation. By the time the Sun formed, about 4.6 billion years ago, the interstellar medium in our neighbourhood had been enriched by several generations of stellar birth and death. The disk that formed the solar system was seeded with the full periodic table of elements, in roughly the proportions we observe in the Sun's spectrum today. Those proportions determined what kinds of minerals would form in the inner solar system, what kinds of ices would form further out, and ultimately what kind of rocky planet would appear in the habitable zone, which turned out to be Earth, with its particular mix of silicate crust and iron core and water, and the thin layer of chemically reactive nitrogen-oxygen atmosphere that is one of the things that makes it unusual, at least among the planets we have found so far. The story of Earth, told from this vantage point, is not the story of an isolated world, but of a link in a chain of cosmic chemistry that stretches back to the first stars. The iron in the Earth's core was forged in supernovae that occurred billions of years before the Sun existed. The calcium in your bones was made in stellar interiors. The oxygen you breathe was produced by early photosynthetic life, which itself was catalyzed by chemistry that had been developing in the oceans for hundreds of millions of years, which themselves formed from water delivered by comets and asteroids that formed in the cold outer reaches of the young solar system. When you understand that chain, when you feel its full length, the discovery of strange planets around distant stars stops being merely academic. It becomes part of the same story. Those worlds are also links in the chain of cosmic chemistry. The iron that reigns on WASP-76b is the same iron that sits in Earth's core, made by the same stellar processes, just in a planet where the conditions allow it to exist as weather rather than geology. The carbon that might form diamond in the deep interior of 55 Cancri is the same carbon that forms the backbone of every organic molecule in every living thing on Earth. The physics does not change depending on which star system you're in. This is the perspective that exoplanet science, at its best, cultivates. Not just a catalogue of strange places, but a deepened sense of connection between our world and others, between our star and the billion-year process of stellar evolution that produced it and will eventually end it, between the familiar chemistry of everyday life and the vast cosmic machinery that generated the raw materials for that chemistry long before any planet existed to use them. There is a quietness to that connection. It does not announce itself. It does not demand anything of you. It simply sits there, in the background of everything, available whenever you choose to notice it. The planets we have been describing, the ones with molten iron precipitation and diamond cores and ring systems, wider than a planet's orbit and atmospheres being slowly stripped away by their stars, are not elsewhere. They are not in some separate universe governed by different rules. They are in the same galaxy, under the same physics, as the planet you're on right now. The same forces that keep Earth in its orbit at a distance from the Sun where liquid water can exist are the same forces that keep WASP-76b locked in its frantic 43-hour orbit at a distance where iron boils. The same force, different conditions, different outcome. The universe is, in a meaningful sense, one place. Enormous beyond any intuitive grasp, yes. Populated by worlds so varied that cataloguing them is a civilization-scale project that will outlast everyone alive today. But one place, governed by one consistent set of rules, producing its variety not through caprice, but through the endlessly rich combinatorics of physics and chemistry and time. When the Roman Space Telescope begins its microlensing survey of the galactic bulge, the dense, ancient central region of the Milky Way where stars have been forming for over 10 billion years, it will detect planetary signals around stars so distant and so packed together that individual characterization will be impossible. It will produce statistical constraints. How many planets per star, how the mass distribution varies with distance from the galactic center, whether the ancient metal-poor stars of the bulge have planetary systems as rich as those in the younger, more metal-rich outer disk. These are questions whose answers will reshape our understanding of when and where in the galaxy planetary systems first appeared. How early in cosmic history the conditions for rocky planet formation were available, and therefore how early the conditions for life might have been present. The answers, whenever they arrive, will extend the picture further back in time and further out in space. They will add depth to a map that has been growing for 30 years, and that shows no signs of reaching its edges. Every new instrument, every new survey, every new technique adds territory to that map and reveals details that were previously invisible. It is a map that will never be complete. The universe is too large, and the time available for observation too short, and the range of phenomena too varied for any finite program of observation to exhaust. There will always be more to find. There will always be planets in configurations we have not yet encountered, atmospheres with compositions we have not yet measured, processes operating in systems too distant or too faint or too geometrically misaligned for current methods to reach. That inexhaustibility is not a frustration. It is the nature of the universe we inhabit. A universe that could be fully mapped in a finite time would be a smaller universe than the one we have. The fact that the project of exploration never ends is a sign of how large and varied and full the cosmos actually is. A kind of abundance that, once you adjust to it, feels less like an obstacle and more like a continuing invitation. An invitation to keep looking, to keep building the instruments that see further, to keep asking the questions that do not yet have answers, to keep turning the page. And so the final image to leave with is not a summary of what has been found. The iron rain, and the diamond cores, and the tidally locked twilight worlds, and the pulsar planets, and the rogue worlds drifting in the dark between the stars, those have all been named and described. The image is simpler than any of those. It is a telescope. Any telescope. A small one on a backyard mount, a large professional instrument on a mountaintop, an orbiting observatory unfolding its mirror in the cold stillness of deep space, and the telescope is pointed somewhere at a star. And around that star perhaps there is a world, and we do not know yet what that world is. We have not measured it, we have not named it, we do not know if it is scorching hot or icy cold, whether it has an atmosphere or not, whether it is rocky or gaseous, whether it is ordinary or extraordinary. But we are looking, patiently, carefully, persistently. With the full weight of a centuries-long tradition of turning curiosity into knowledge, asking the question that has no final answer. What is out there? The galaxy, as best we can tell, is answering. Quietly, in the language of photons and spectral lines and transit depths and Doppler shifts, it has been telling us about its worlds for 30 years. We are getting better at listening, and the more carefully we listen, the stranger and richer and more full of possibility the answer turns out to be. If this kind of exploration, this slow, careful, patient unfolding of the universe's strangeness, is something that resonates with you, then consider staying close to this channel. There is always more of the cosmos waiting to be looked at together. Subscribing means you will be there for the next question, the next discovery, the next world that turns out to be something nobody predicted. The universe keeps building extraordinary things in the dark, and we will keep pointing the telescope. What changes when we look, when we genuinely, carefully, patiently look, is not the planets. It is us.